Okay. So now we want to determine the internal shear force and bending moment at a section at C. So I think a good idea would be to initially just, if you need to do this graphically, just draw a line through C. And imagine drawing a free body diagram for the left side and then another one for the right side, and which one do you want to work with? I don't see a real advantage to either way. Both sides have uniform loads on them. Both sides have at least one reaction. The pin at the left would have a horizontal reaction, but since there's no horizontal force, that's going to be pretty easy to find. So there's really no difference. So I'll just go left. Why not? So if I'm going to go left, I need to find my reaction at A. So I'll go ahead and assume that I have a reaction, AY acting up, and a shear force, an axial force here. I'll go ahead and show that I have a BY force acting up also, but I'm not going to be too concerned about that one. Now remember, since I'm going to, my goal is to draw a free body diagram for the left side, so I need my reactions at A. So how do I get those quickly? Some moments at B. So we'll do that. If I sum moments at B, AX will pass through B, and I'll get AY right up. So let's do that. So I like to use right-hand rule. So right-hand rule, and I'm going to sum moments at B. Make sure it's in equilibrium. Now this distributed load is a little difficult to deal with in this form. So we're going to make a force that's equivalent to it and have it pass through the centroid. So it's a rectangle. The area of a rectangle is just the base times the height. So the base is 18, the height is 3, so what is that? 54. So I'll show that it's an equivalent force by using a double line. That'll be 54 kips, and it'll act through the centroid, and the centroid of a rectangle is right in the middle. So this is 18 feet, so that should be 9 feet from either end. So when I sum moments about B, this equivalent force, 54 kips, is going to create what kind of moment about B with my sign convention? Looks like it's going to be positive. So the force of 54 kips, the distance from B to the centroid is 9. So there's the moment about B created by the distributed load. In response to that, the reaction pushes up, it looks like. That creates negative moment. The force is AY and the distance is 18. So it looks like AY is going to be 27 kips. That's not surprising. This uniform load, 54, you'd expect half to be held by A and half to be held by B. And that's what I got. 27's half. Technically, I should show that if I sum forces in the x direction, all I have is AX, and therefore AX is 0. So now I have all my reactions. So now I can go and draw my free body diagram for my section here, which I'm going to call AC, from A to C. And I'll maybe make it just a little bit bigger. All right. So first I'm looking at A side. I found AX was 0. I found AY was positive 27. I assumed up, so that's going to be acting up 27 kips. This piece, AC, is 6 feet long, and it has a distributed force on it. The force was given as 3 kips per foot. So what's the concentrated equivalent of that?
18 kips.
Yeah, it's another rectangle, base times height, so that's 6 times 3. That should give you 18. And again, it acts at the centroid, which is half the distance. Half of 6 is 3 feet. Now at the cut side, the C side, this is where I'm going to assume positive axial force, positive shear force, and positive bending moment. So think about those for a second. Axial force, that one I think is good. As you pull away, this element would obviously get longer. That's positive. The shear force is pushing down, so my little element, when I push it down, wants to rotate in what direction? Clockwise. Positive. And if you held up your little stack of paper here and you twisted this way, it would twist up. That's just half a smile. Positive. So that looks pretty solid to me. So now I just need to write my equations to solve for this. And like we mentioned before, since the axial and the shear force pass through that center point of the cut, that's a good place to do the moments. So we will sum our moments at the cut, make sure it's in equilibrium, and use right-hand rule for our sign convention. So starting with the internal stuff, this moment, using right-hand rule, is positive or negative? It is positive. The equivalent force 18 about the cut is going to go positive sign convention. So that'll be positive. The force is 18 kips, and the moment arm is 3 feet. Then way out here on the end is my reaction force. About the point C, it's going to go clockwise, so that's going to be a negative moment. And it has a magnitude of 27 kips and a distance of, looks like 6 feet. So what is the moment at C? $100 and what?
108.
108. Anybody else get 108?
Yes.
Yes? Yes? Positive or negative? Positive. So that would be kip feet. Now, does it make sense that C would have a positive bending moment? I don't know. Let's go back up here. How is this thing going to bend? It's probably going to bend something like that. And what is that? That thing is smiling all day long. So there is not a place on that structure that's not positive bending moment. There is no negative bending moment in this structure at all. Now there's a couple places where there is zero moment. What's the moment at a pin connector? Zero. What's the moment at this pin connector? Zero. So if you had to draw the variation of moment, you would start at 0, do something. At C, you would know it as positive 108. Then it would probably go down and get smaller and smaller back to 0. When we start drawing shear and shear force and bending moment diagrams, that's going to be important to know where you start and where you end. All right, so we're almost done. I want to get the shear force now, so I will sum forces in the y direction. I like to assume up for my forces to be positive, so I do that again. And then looking at my forces on my shear diagram, on my free body diagram, the shear force is down, so that's a negative force. My 18 kip is down, that's a negative force. And my 27 is up, that's a positive force. So what's the shear at C? Looks like it's 9. We have positive shear at C. And just to be complete, I'll sum forces in the x direction to make sure I have equilibrium there. And the only force I have in the x direction is AC, which you can then see is, by definition, almost 0. And that's it. Pretty cool, huh? So now if you had to design this beam, and I was really worried about something going on at C, you would know that, hey, I've got to have a beam that has the capacity of this moment and this shear, at least at that point. Is that the maximum moment and maximum shear in the beam? I don't know. Probably not. Probably not. We'll find that out later. All right, any other questions?
On the previous example, the only reason we made two separate cuts was because we had that point load.
Yeah, I was just trying to demonstrate that that point load would show a unique change in the shear diagram.
Okay.
That's an interesting point here. If I made this point C and I moved it 1/1000th of a centimeter to the right, what would change here? Hardly anything. Right? Because it's a distributed load. It's really not making much difference. If there was a point load at C, though, you'd see a big change in the shear as we moved, again, from the left to the right. And I always do left to right because our sign convention for X is we usually start on the left of the beam and we move to the right, and we call that positive. So we'll probably do the same thing. We'll write our equations in that way. We'll draw our diagrams that direction. We don't usually start on the right and go to the left unless it has some advantage, and usually there's not much to it. Okay. That one only took 11 minutes.